If I want to show that these graphs are not the same thing, then I need to find some property that they differ by. And that property can't be something that's disguised. For example, if edges are crossing, it is usually possible to redraw the same graph and take away the crossing. It doesn't make it a different graph, it's just drawn differently. So edges crossing is not a legitimate way to show that things differ. If we look at G and H here, you could say on H, there's a degree 1 vertex on the right-hand side, and on G, there isn't. Well, again, that's not any good because that just has to do with how I oriented the picture when I drew it. Let me summarize this. I want to show they're not isomorphic. So I'm going to do this by a pretty standard order of checking things. So step 1, compare the sizes. There are two sizes involved in this graph. There's the number of vertices and the number of edges. We're looking at these two graphs. The one on the left has 7 vertices. The one on the right has 7 vertices. The one on the left has 8 edges. The one on the right has 8 edges. So they're the same. The next thing to check is the degree sequences. The degree sequence is what you get if you list all the degrees and then you sort them from smallest to largest. The reason you have to sort them at the end is that the order in which you list the degrees isn't actually important. All that matters is they both have a degree 4. They both have 2 degree 3s. Things like that are important, not how I organize the data. So looking at graph G, I'll just do an alphabetical order. So it has 1 for A, degree 3 for B, degree 2 for C, degree 1 for D, 2 for E, 3 for F, and finally for G. Those are the degrees for graph G. Now let's look at graph H on the right-hand side. Q is 1, S is 2, R is 3, V is 2, W is 3, T is 4, and finally U is 1. So those are the degrees of graph H. I want to show that it's the same as graph G. So I will compare those degree sequences. As I said, it's not good enough to compare the order because the order is arbitrary. I could have read off the values in a different order. So if I sort this from smallest to largest, I get the following 6 values. And if I sort the H case, I also get 2 1s, 2 2s, a 3, and a 4. So these seem to be the same. I'm always going to require a third check. Just look for something else they seem to differ at. How about I look for the smallest cycle I can find? Here there's a triangle, that's a degree 3. Here I have a triangle on the right, degree 3. Size 3. The technical term is a K3 subgraph. It just means that inside of that graph, there was a K3 hiding. So we've passed 3 different tests, and in all 3 cases, the 2 graphs were the same. This does not mean they're the same. This means they're a good candidate for being the same, and maybe you should try to match things up. You can try to match them up, and you'd get the answer we found before, which is that we found an isomorphism to pair things up. So let's look at another example and ask, are the following isomorphic? Okay, so I want to find out whether or not these graphs are isomorphic. Count vertices and edges. So looking at the graph on the left, it has 2, 4, 6 vertices. Counting edges is trickier, but it has 3, 4, 5, 6, 7, 8. Looking at the graph on the right, it has 6 vertices. And then if we count edges, these agree. Now we move to degree sequences. So on the left one, I'll start here. So it would be 2, 4, 3, 1, 3, 3. And then you sort them from smallest to largest. And now look at H. The degrees there were 1, 4, 4 at the top, 2, 2, 3. So I'll sort them from smallest to largest. And we notice a difference. On the bottom example, there was this 2 when there should have been a 3, and a 4 when there should have been a 3. So these are not the same graph. I discussed how somebody could draw the figure differently. Well, this is saying that no matter how clever you are about drawing the figure on the right-hand side, you can never pair it up exactly with the one on the left.